the Large Magellanic Cloud. This work being led by Marta Sawillo in the research group that I oversee. But today I'm talking to you about that. I'm talking to you about the mission that I oversee as the senior project scientist, which is the Hubble Space Telescope. And so I want to tell you a little bit about the status of Hubble. This is a non-technical talk, and how it's correlating with the Webb Space Telescope and other facilities. I know many of you probably mainly use ground-based facilities, so we do a lot of complementary work with ground-based facilities as well. But this is kind of a Hubble and Webb-centric talk. Everything okay? Yeah. It looks like it's on. Let's see. Well, let me. Okay, my camera is not on, and I will allow that. I think I'm still sharing my screen. Yes. So I think I'll just go back into. You know, they say if we can send people to the moon, why can't we, share screens? Things like that. Okay, but I don't know if I'm supposed to be standing in front of the camera here or. Okay. All right.
Yes. Thank you, Night. Now
okay. So I work at the NASA Goddard Space Flight Center in Greenbelt, Maryland. Have any of you ever been to Goddard or worked at Goddard? A few? Okay, great. So Goddard Space Flight Center is one of NASA's 10 centers. And Goddard focuses on science, so on astrophysics, heliophysics, planetary solar system work, and earth science. So the missions that we do typically are science oriented and always space based. We have a different agency in the US that manages the ground based telescopes. That's the National Science Foundation. So NASA thinks about things that are in space, and it's a very large institute, probably the largest, one of the largest astrophysics and space science institutes in the world. There you can see Hubble. Isn't it beautiful there? So Hubble is a joint mission between NASA and ESA. And in case you've forgotten, here's a few of the stats. It was launched in 1990. So it's 34 years old, which is probably older than some of you in the room. And it was deployed from the space shuttle. And it's in low Earth orbit, which means it's not very far up. Right now, it's at about 550 kilometers above the surface of the Earth. It's slowly, naturally decaying in that orbit, so that's something we have to think about for future years. It's moving very, very fast, 17,000 miles an hour, which is what, 27,000 kilometers per hour. So it's moving very fast because to stay in low Earth orbit, of course, but we have very good pointing control, so you can still, fix on a distant object and keep pointed, even though we're moving very quickly. We have a great engineering background for this telescope. It's solar powered, as you can see, so the panels are always recharging the telescope. And so we've become accustomed to these beautiful pictures, which is of course why we put telescopes in space. But it's incredibly important for science, right? This is the interior of a globular cluster, Omega Centauri, and because we can resolve the individual stars, of course, we can not only see how beautiful it is, but we can also do individual spectra of individual stars and get their SEDs and other information and find out something about the stellar population. So obviously, getting better resolution gives you better science. And here's just some another beautiful image. This is a carbon star, CW Leonis, I believe, that you can sort of see the episodic atmospheric expulsions from the star. And it tells you, of course, something about the nature of the star. But what I love about pictures from telescopes like Hubble is what you see in the background, right? You also see fantastic views of other galaxies. So we've become accustomed to this. And just to remind you that both NASA and ESA have a whole fleet of space telescopes that are either operating or are in development or will be operating in the future. This is the suite of astrophysics missions swirling around like a spiral galaxy here. But Hubble is the oldest operating mission that's still operating. And you might recognize some of the other facilities here in different wavelength bands. Some of them are in cooperation, of course, with other agencies like Euclid. And then we have some very small missions too that are being developed, that CubeSats and smaller, that are being launched and are very successful. ESA has its own cosmic vision of current and future missions, and I won't go into all this, but this was presented last week at this conference in Porto on science with Hubble and Webb, and how these telescopes fit in with the other missions current and planned from ESA. Okay, so we've become accustomed to beautiful images. I particularly like the star formation views. This is, of course, a massive cluster, and it, as we know, interacts with all the surrounding material in these regions where outflows and radiation from massive stars, the radiation ionizes the surrounding gas, the winds and outflows blow away wispy gas, leaving behind the denser material longer. It's always sort of pointing back to these massive stars because it's protecting this wake behind a dense clump. And it's in these dense pillars that we expect the lower mass stars to still be forming, of course, because it takes longer for them to form. So what we've learned for over the years from these telescopes is that star formation, everything that we study is very active. The universe is dynamic, studying the interactions of stars, their feedback on the environment, studying how enrichment over billions of years from star formation has enabled planetary systems to form in our own epoch. So we've learned much over the decades that we've had Hubble. And just to give you a little history here, the idea of putting a telescope in space goes back many decades, but it became serious in the US when the National Academy of Sciences had an official study led by Lyman Spitzer on the scientific uses of having a large space telescope. And then the momentum for this was really picked up by Dr. Nancy Grace Roman. She was the first astrophysics leader at NASA headquarters back in the 1970s, really a pioneer. And she pushed the idea that NASA should take the lead in sponsoring a space telescope. So she put out in 1977 the first announcement of opportunity for scientists to be involved in the development of this large space telescope. So she's sometimes called the mother of Hubble. And the next big space telescope that we are launching in probably 2027 is named after her. It's called the Roman Space Telescope. You may be familiar with Roman. Okay. So why do we have Hubble why we had Hubble for 34 years? Well, in part, it's because we've had astronauts returning to the mission time and time again. So 5 times since its launch, astronauts have returned to the mission. It's very dramatic. The space shuttle docks with Hubble in low Earth orbit. The robotic arm built by the Canadian Space Agency would grab onto Hubble, pull it into the cargo bay. Astronauts would come out for several days, several hours at a time in their, extravehicular suits to go out and open up sections of the telescope to repair electronics or to replace science instruments and upgrade the telescope. So we basically had a new telescope every time the astronauts have gone to do this. And the last time they did this was in 2009. but they did such a wonderful job that the telescope is in very, very good condition right now. We're probably at the peak of our scientific return right now, even after 34 years, thanks to the astronauts, but thanks to the years and years of work from people on the ground who have developed those science instruments, built them, orchestrated the interchange between engineers, astronauts, and scientists, and of course, keeping the public and those who support the mission in the government informed and excited and part of the whole enterprise. So having a large successful mission like this takes a lot of players working together to orchestrate the support and to navigate these different cultures. The culture of engineering and human spaceflight is different from the culture of science. And so I got to experience some of that myself as I was helping in the preparation for this last servicing mission, trying to navigate as a science communicator between the way scientists think and the way engineers and the human spaceflight program thinks. And they're different cultures, you know, so that was an interesting challenge. So here, to celebrate the 34th birthday of Hubble, we just released an image of the Dumbbell Nebula, which is an aging star. And of course, as stars grow older, they begin to expel their outer atmospheres. And this one is doing it in a kind of bipolar bubble fashion. So it's quite pretty. So we can say a happy 34th birthday to Hubble. Okay. This was our picture last year of NGC 1333. All right, so Hubble is doing all kinds of astrophysics. It was designed as a general purpose observatory, so we don't focus on any particular type of astrophysics. We listen to what the science community from around the world wants to do. So we've been doing science and everything from solar system work to stars, stellar population, stellar physics, the interstellar medium, the intergalactic medium, galaxies, of course, exoplanets, which we didn't even know about when Hubble was designed. So, of course, we are using the telescope now for types of science that were not envisioned when Hubble was built. So there's a lesson there that you have to be adaptable to changes in the priorities of the science community. And of course, indirectly, we're studying things that you can't see, but we can see the effects of, like black holes, dark matter, dark energy, and that all feeds into our understanding of cosmology. Hubble's in good technical condition. It's even now at the peak of its scientific return. You may have heard about or used some of the science instruments on board, including the older instruments, the Space Telescope Imaging Spectrograph, or STIS, the Cosmic Origin Spectrograph, which is a very sensitive ultraviolet spectrograph. We're using two of the cameras right now, the Advanced Camera for Surveys, which is an older camera, and the Wide Field Camera 3, which is the newer camera put on board in 2009. WIF C3, for example, is panchromatic. It sees ultraviolet, visible, and near-infrared light. STIS also sees visible and infrared, both near-infrared and far near ultraviolet and far ultraviolet light. So we cover a swath of wavelengths. And as Hubble ages, we are forging innovations, both in how we use the telescope and also how we mitigate the aging of some of the instruments. For example, the detectors on COS, the Cosmic Origin Spectrograph, are losing gain naturally as they do over time, but we're learning to use different parts of the detector to keep its sensitivity as high as possible for as long as possible. So we have a team on the ground that's constantly looking at the health of the science instruments, thinking about different ways of using them that will preserve them the longest. The scientists themselves around the world are figuring out innovative ways of using Hubble, such as a new spatial scanning mode that increases signal to noise when you're trying to very, very carefully gauge the flux of a particular source. So innovative uses of Hubble, both by scientists and by the team on the ground, are helping to enable this mission to continue successfully for probably quite a few years to come. We also have challenges with its pointing control system. So We normally need 3 gyroscopes to point Hubble, but one of our gyroscopes, we had 6 new ones put on back in the last servicing mission. 3 of them have failed since then, naturally. The other 3 have a different design that makes them last much longer. But one of those 3 that we have left is very unstable. And so if we have to, we can turn that one off, and we know how to point Hubble even with just 1 gyroscope, because this innovative team has learned how to balance 1 gyroscope with fine guidance sensors and other things to still give us an accurate sense of pointing. So technical innovations is a very, very important part of keeping Hubble successful as it ages. And that's one of the takeaways here, that I don't know what kinds of facilities you use for your work, probably a variety in this room, but all those facilities have to grapple with this question: how do you, if it operates for a long time, how do you keep it successful? And that's the name of the game for Hubble in these days. Okay, I want to switch now to saying a little bit about Webb. Have any of you ever actually used Hubble or Webb for observations, data, pulling from the archive, anything? All right. Okay, very good. You will, because all the data is going in a wonderful archive, and you can all access the archive. So here was the launch of the James Webb Space Telescope. James Webb was the leader of NASA back in the 1960s during the Apollo era. And he very much wanted NASA to be a science agency as well as just building rockets. So he was a supporter of science. So this telescope was named after him, the Webb Space Telescope. And there are some excited but a little bit nervous NASA and ESA officials there at the launch, which took place in South America on Christmas Day back in 2021. The Webb telescope looks like this. This is what the mirror looked like in the Goddard Space Flight Center clean room. And it was really interesting because I loved going and looking through the window to see this huge segmented mirror being put together and the science instruments being attached to the whole facility. The mirror is 6.5 meters across, which sounds like nothing to radio astronomers, but to a space-based astronomy, this is a very big telescope to launch in space. And because it would not fit into the fairing of the Ariane 5 rocket, it had to be built so that it would fold up and then unfold on its way out to L2 where it was going. So this was a very challenging engineering task. Webb is like Hubble. It has several science instruments. It has both cameras and spectrographs, as well as a coronagraph capability so that you can block out starlight to look at circumstellar material and disks and so forth. So it's a multifaceted facility, but it is not in the same location as Hubble. So this is not to scale, mind you, but Webb is, so Hubble here is in low Earth orbit, and at about 570 and getting lower every day kilometers altitude. Webb is at well over 1 million kilometers out. It is not orbiting the Earth, it's orbiting the sun along with the Earth. And it's actually doing a small orbit around its position at the second Lagrange point. So it's a long way away. It was not designed to ever be serviced by astronauts. We might, either for Webb or for future telescopes at L2, be able to send robotic servicing spacecraft out to do simple servicing tasks if the telescope is built with modular equipment so you can pull out something easily with a robot and put something new in easily. It's put that far away to really shield it from interference from the Earth, but also these sun shields are always between the telescope and the sun and the Earth and the sun to keep it cold, because Webb is an infrared telescope, very sensitive, and needs to be kept very, very cold. So you probably have seen some of the amazing first images from Webb, where you see this brilliant contrast between the radiation coming from massive stars off the top of this image, impacting the edge of the surrounding molecular cloud, a dusty cloud, and of course there's ionization of the gas, but there's also structure formation, and again a whole set of these pillar-like things pointing back to the massive stars, and we expect the lower mass stars to be forming within this region, and in fact they are. So there's a lot of study here in the Carina Nebula of low mass protostars that are still forming. But this was just a beautiful public release image. And of course, I love protostellar jets. That's my own field. So here is an image of one of these spectacular bipolar protostellar jets, the Herbig-Haro object HH211. The protostar is buried down here in this dense circumstellar disk, but the jet that you can see in infrared is just spectacular, and you can see the bow shock regions as the jet has several episodes of expulsion, of outflow. So Webb is studying everything from star formation to distant galaxies and is very successful so far. So how do these compare? I've already mentioned to you that they're in at different distances. Let me see if I can get this to they look different. They're designed to receive different kinds of wavelengths. You can see how big they are. So the Hubble telescope is about the size of a city bus. And so then many ask the question, do we need both of these telescopes now? And does the Webb telescope actually replace the Hubble telescope? So you need to answer these questions correctly before you pass today's seminar. Okay, so do we need both? Does the Webb telescope replace the Hubble telescope? You pass. Okay. All right. Yes. All right. All right. So one reason, of course, is that they see different wavelengths of light, and you know this. But Hubble is designed to see the visible spectrum and bluer than blue, the ultraviolet light. In fact, you have to be in space to see most ultraviolet light, which is really important for astronomy. Hubble sees into the near infrared part of the spectrum. The Webb telescope sees red visible light and all the way through the near infrared and into the mid infrared part of the spectrum. So they see different wavelength bands, and these are complementary to each other, and we're taking strong advantage of that already. In fact, last week at this conference I was at for science with the Hubble and Webb, we saw countless examples of how the scientific community is using both Hubble and Webb together to get better understanding of everything from exoplanets to star formation to galaxy evolution. And that's exactly what we'd hoped for. So here's, for example, the famous Eagle Nebula, one of these regions with the pillars pointing back up to a massive star forming region. But Hubble is very good at seeing the reflected light in regions like this, but Hubble cannot see into the dust. So you can see the structure, but not the activity. Hubble can see a little bit of the infrared emission, which gives you a hint that in infrared you can see through some of that dust and see more stars. Webb looked at this picture and saw in a different field of view, a different orientation, but of course is seeing a lot more stars, seeing a lot of this pillar-like structure down here, seeing into the pillars. If we look at side by side, you can see that Hubble gives you a better sense of the overall structure of the pillars. Webb gives you a better sense of what's going on inside and through the dust. You see a lot more stars in the whole region, and you see these hot spots, especially at the tips of these pillars, where protostars are beginning to coalesce and heat up. So complementary work, and of course we're anticipating that Webb will be doing much more of the analysis of the composition of these clouds, the environments where these stars are forming, which is what my team is doing as well. So, you know, the public has been very interested. Do we need Hubble now that we have Webb? And so here's a story that came out in 2022 from a magazine called Business Insider that says the Webb Space Telescope is astronomy's shiny new toy, but the Hubble Space Telescope isn't old news. It's at its scientific peak. And here's an article that came out in Nature of why the Hubble telescope is still in the game, even as JWST wows. So I'm going to focus a little bit now on what we're doing with Hubble scientifically in different areas, because that's my focus at NASA is being the senior scientist, oversight scientist for Hubble. We want to make sure we're using Hubble in the best ways we can to get the best science out while we still have this asset. And really the most powerful science return comes when we use Hubble and other assets in space and on the ground in complement. That gives a lot of power to science that you can't get from any one of these facilities alone. These are just example facilities I've shown you. There's Hubble, but of course there's other telescopes in space. These are the Keck telescopes in Hawaii and ALMA in South America as just examples of different kinds of facilities. We're continuing to plan to use Hubble and its complementarity with other facilities for all types of astrophysics. So we're still trying to use Hubble for the full range of astrophysics, but we are also adapting a bit to the changing priorities of the scientific community, and I'll say a little bit more about that. But the two of the highest priorities in international astrophysics now, which was not the case when Hubble was launched back in 1990, but now two of those hot topics are, of course, studying exoplanets and planetary systems, and studying multi-messenger astronomy and time domain astrophysics. So, for example, looking at transient events, whether they are supernovae or merging neutron stars, these create electromagnetic radiation at times that Hubble can pick up, and we can study the details and sometimes correlate with other messengers, such as a gravitational wave detectors when we have two merging massive objects like neutron stars or even black holes, if there's enough circumstellar material to create an electromagnetic signal that Hubble can pick up. So we're focusing a lot on these things, cosmology, exoplanets, but whatever the scientific community is prioritizing. And of course, NASA itself has a strategic vision, as does ESA, for what are the hottest topics that our facilities should be addressing. And these are the main questions in our long-term strategic plan for NASA, which is, are we alone? How did we get here? How does the universe work? Hubble is designed to answer those types of questions. All right, let's start with the solar system a little bit here. So here are some beautiful images from Hubble, Jupiter, Saturn, Uranus, and Neptune. But we've had Hubble operating for decades, so we've been able to look at these planets over and over and over again. Right? So when you have a long time baseline, you can study time varying phenomena, and in the solar system, that can include things like the weather on planets, and in particular, the great red spot on Jupiter. Over the decades, Hubble has noticed that storm is shrinking, and not only is it shrinking, but it's getting faster. The winds are speeding up. So you need the long time baseline to understand that. Other storms are cropping up. This storm seems to be fading. Learning about planetary atmospheres. Here's another situation. So we have Neptune, but because we've observed Neptune over decades of time, we've seen in the top blue row there with Hubble, you see these clouds on Neptune that come and go and come and go. Well, now we've compared that with the solar cycle. So this is solar ultraviolet radiation over decades. And of course, the solar cycle has a period of about 11 years. And so we've noticed that as the solar cycle rises and falls, the cloud production on Neptune rises and falls with a little bit of delay, just as you would expect, because it takes some time for the UV and the particle radiation from the sun to get to Neptune. So having this, now we need to understand the physics, what's actually happening. Neptune's a long way from the sun. So what is it that's coming in these advanced solar cycles that that stimulate cloud production in Neptune? These are the kinds of trends you can have when you have a decades old archive. And we have a wonderful archive that anyone can access and find time transient phenomena and sequencing like this. We are also working in collaboration with other missions. So here is an example of looking at Jupiter's storms, but using different missions to do that. So Hubble can see the reflected tops of thunderstorms, if you will, on Jupiter. But other observatories can see what's going down inside these storms. So Gemini can pick up the thermal infrared deeper into the atmosphere. The Juno probe is at Jupiter orbiting, measuring in situ there the magnetic and gravitational fields around Jupiter. And Juno can pick up radio waves that's being emitted by things we might call lightning from deep within these storms. So when you have three different ways of looking at the same phenomena, again, the synergy gives you a lot more information. And we used Hubble also in complement with the DART mission. The DART mission was designed to intentionally impact an asteroid to see what would happen to it, just to try to understand if we could potentially alter the trajectory of a future dangerous asteroid. So Hubble saw the initial debris from the impact of the DART mission on Dimorphos, but then over the many months since that impact, we've seen little boulders moving slowly away. And so it's teaching us something about the composition of asteroids like Dimorphos, but it's also showing us that possibly impacting this type of asteroid is not the most effective course of action, because you just create a swarm of material that might be worse than your original problem. So these are the kinds of things. There's a lot of study that still needs to be done. The point here is that using Hubble in complement with other facilities, like in this case probes, gives us a lot more information. And while we're still here in the solar system, let me just say that Hubble is the only large, flagship, what we call the largest mission scale observatory that can observe ultraviolet light, but from now until perhaps the far future. So here's another gorgeous view of Jupiter in visible light. But if we add the ultraviolet light from Hubble, you start seeing the auroras, the northern lights, as we call it, on Jupiter, and that helps us understand the magnetic fields, the strength of the magnetic field, and how the magnetic field is varying on Jupiter, which I think is quite cool. And here's just an infographics to show a selection of major observatories, space observatories, and the ELTs on the ground in the coming decade and their wavelength coverage. So most of these, as you move from Webb to the upcoming Roman telescope, the ELT ground-based telescopes, including the Rubin Observatory in South America, and even Euclid and Hubble, most of them see visible light and a little bit into the near infrared. But then you've got Webb going far into the mid-infrared from space, and Hubble going into the ultraviolet. So this is important for their unique capabilities in this whole spectrum of capabilities. And I I want to point out that we're trying very hard to do what we can with Hubble while we still have Hubble to gain as much ultraviolet data as we can and have it in the archive so that people can use it for many years even after Hubble is gone. So one of those programs is called Ulysses, where for several years we've been taking spectra in the ultraviolet of stars in our massive stars in the Milky Way and in nearby neighboring galaxies, and also T-Tauri stars that are often variable because they are accretion sources. And so this whole observing project has just ended. We have hundreds of spectra now in the ultraviolet in the archive, easily accessible. And now the work actually begins. You know, for perhaps decades into the future, these ultraviolet spectra of stars can be used for all kinds of research and in correlation with other wavelengths, observing stars, observing their compositions, their environments, and their variability, especially when it comes to the protostars, the T-Tauri stars that are accreting. As I mentioned, we're also using Hubble to characterize exoplanets. That's something Hubble wasn't originally designed to do, but Hubble was really the pioneer in understanding how you could use transiting planets. In this case, this is an artist's conception, but of a real system that was discovered by the Kepler Observatory, to understand something about the atmosphere of the exoplanet, because as the exoplanet orbits in front of its parent star, some of that starlight comes through the outer parts of that exoplanet's atmosphere, and you can understand some of the composition of that atmosphere by what's absorbed. You can understand the size of the planet by how much light is blocked by the planet from its parent star. And so Hubble and Webb are not good finder telescopes for exoplanets because they have a very small field of view. But once another observatory finds an exoplanet, Hubble and Webb are very good at doing follow-up observations. So here's an example. This is a gas giant exoplanet, WASP 39b. This was the Hubble spectrum taken of that planet. And you can see here evidence. The actual data points are in yellow. The model is in blue. You can see signs of sodium, potassium, and water vapor. But when you get to this side of the spectrum, we can't really tell if we're seeing carbon dioxide because Hubble can't see that far into that part of the spectrum. These two data points were from Spitzer, which was a good infrared telescope, but very, very limited in what it could do compared to Webb. Now we have Webb looking at that same exoplanet in those hard to reach for Hubble wavelength bands, and you see a very clear signature of carbon dioxide. So when you can combine the Webb and the Hubble spectra, you get much more information about the composition of exoplanets. And so we'll continue to work on that in that realm. We have been working in complement with TESS, which is another exoplanet finding space telescope. And TESS has, in some cases, found evidences of a transiting planet, but can't quite discern whether what they're seeing in terms of starlight dipping regularly, as you would see when you're looking at the starlight as a whole, whether that's because there's one planet crossing the midpoint of that planet, or whether there's a binary star system and maybe the exoplanet is just grazing one of the stars. It's a little hard to discern exactly what system is you're looking at because TESS could not resolve the individual stars in a multi-star system. In this case, Hubble was able to resolve individual stars and resolve the discrepancy so that we knew, at least in this particular system, that what they were seeing was a transiting Earth-sized exoplanet. So that's a very exciting discovery, but it was only enabled by Hubble and TESS working together. I need to ask my host, are we to be done at 1 o'clock sharp? I will. I will. I'll whiz through. We also can do some direct imaging of exoplanet formation. So here's a Hubble image of an exoplanet being formed, because you can actually see its accretion in the ultraviolet as you block out the starlight. So I think that's really amazing. And Webb is beginning to do some direct imaging of exoplanets as well. It's very hard to directly image exoplanets, but we're doing this the best we can with Hubble and Webb. And future observatories will have a better capability of directly imaging, hopefully Earth-sized exoplanets. Okay, I'm going to whiz through the rest of the universe very quickly. So we're, of course, looking at other galaxies, and this is one of my particular favorites, NGC 1309, just because it's beautiful. But, of course, we see different things when we look in optical light. Here's a different galaxy. I believe this is the Whirlpool. The optical light from Hubble shows you star-forming knots in purple. These are ionized nebulae where you can see they are hotspots of massive star formation, but they're interspersed between these hidden and behind sometimes these lanes of dust in the spiral arms. Well, the Webb telescope actually picks up that dust, right? The dust is glowing in infrared, so you can compare what Hubble sees and what Webb sees to get a full information of star formation and their environments, particularly in the spiral arms of star-forming galaxies. Here's just another beautiful pair, Hubble and Webb side by side in NGC 7496. And if you haven't gotten the point already, here's another combined galaxy in NGC 628, where, again, Webb is beautifully pointing out the warm, heated dust and dust lanes. Hubble is pointing out the regions of star formation that are between and behind some of those dust lanes. And so together, of course, you get much more information. And more recently, I think this is just beautiful, but this is a Euclid picture of the Horsehead Nebula with visible and infrared light. Hubble has actually seen that in more detail in its infrared capability. But then when we blow up that edge region with Webb, you can actually see the interface of where stellar radiation is shaping and ionizing the actual edge of the Horsehead Nebula. So a beautiful comparison there. Okay, I'm going to just go quickly through this. Hubble and Webb, interacting galaxies. When you have a collection of galaxies that are actually close enough to each other that they're interacting, you can start to see how they're pulling material off from one to another, and how star formation is actually induced by galaxy interactions. I'm going to flip through some of these comparison images again. Lensing is something that's really very important, of course, for cosmology and for understanding dark matter as well. So here is a Hubble image of a cluster of galaxies, but of course you can also see the arced shapes of lensed galaxies in the background. The light coming through this cluster of galaxies and being magnified and distorted by the dark matter. So we're using these to make maps of dark matter distribution based on the distortions of the background light. But we're also using this phenomenon to understand the background galaxies themselves. So here's one of these extremely high redshift magnitude galaxies. I think this was something like a Z of 11, 10 or 11, something like that. And of course, it's messy looking, but you can start to resolve individual spots of star formation in an extremely highly redshifted galaxy. And we can only see it because it's being magnified. And sometimes you can actually see an individual star in a background high redshift galaxy that's being magnified and stretched out. And that is the case for this particular star called Arundel. Webb has seen it too. I'm rushing through this, but if they happen to fall on the particular caustics of the gravitational lensing in front, the magnification lines, then sometimes you can actually see individual stars from very high redshifted galaxies. Okay, so as we move forward, you're all familiar, of course, with these extremely beautiful deep fields. They enable us to understand galaxy evolution as we look at some of the most distant galaxies and compare them to galaxies closer to us in space and time. Hubble's going to continue to do studies of cosmic history, galaxy evolution, looking at the activity within AGNs, black holes, circumgalactic and intergalactic medium, and also the indirect studies of dark matter, dark energy. We're continuing to refine the Hubble constant and look at that tension between what we're measuring in the nearby universe regarding its expansion rate with Hubble and Webb versus what is predicted from early universe measurements with Planck. And then we, as I mentioned, are looking at transient phenomena and will in the future years. For example, it wasn't too many years ago, 2017, that there was a kilonova observed, which seems to be the result of a merger of two neutron stars. Hubble was able to find out where that explosion took place in the context of its parent galaxy. So it's really important to not only detect that you have particles, radiation, and gravitational waves coming from some general area of the sky, but then with Hubble actually honing in on the position within its parent galaxy, and you can see the fading of that kilonova explosion over several days. This all correlating with the gravitational waves that were emitted by that same episode and picked up by LIGO and other gravitational wave facilities. I'll just say quickly that Hubble and Webb are continuing to look at galaxy evolution, as I mentioned, by comparing the very distant galaxies, which are outlined in red circles here, with the more nearby ones. And by doing so, you can see how galaxies have, in general, changed over cosmic history. They've grown larger through mergers with their neighbors. They have had generations of stars coming and going in these galaxies, so that ones closer to us, as most of you know, are more enriched and have higher metallicities. And so trying to understand that whole evolution of the universe over cosmic time is something that Hubble has been focusing on, but Webb can see deeper into the universe because it can see even the more redshifted light from distant galaxies than Hubble can see. And so here is the deep field, a deep field from Webb. And when you put them together, you can really get a nice sense of the very distant galaxies that Webb is picking up, which are colored in red here. The more nearby ones that Hubble is picking up, which are colored in blue, the intermediate ones in white. And of course, by studying the characteristics of these galaxies from the highest redshift epochs to intermediate redshifts and to our own, we really are getting a much better sense of galaxy evolution, of cosmic evolution. And it's thanks to having both Hubble and Webb together. And you may be aware that Webb is finding out that some of the highest redshift galaxies are very powerfully forming stars. They're very bright. The star formation is intense. The light to mass ratio is high. So that was kind of a surprise that star formation and galaxy formation seems to have started very early on within the first few hundred million years of the universe. All right, as I close, I'm going to just mention that the publication rate for Hubble continues to be strong. We're also making innovations in other things, how we're choosing proposals. We started something a few years ago called dual anonymous peer review, so that the panels who are reviewing proposals for Hubble do not know what teams have actually made those proposals. And of course, the proposers don't know who is reviewing them. They also don't know what institutions they're from. And this was designed to mitigate any unconscious bias that review teams might have toward certain teams or certain institutions or any kind of gender bias or anything. What's been amazing is while this new process was put in place, it has mitigated some of those biases, for example, gender bias and so forth. But what's really been amazing is that it has increased the number of proposals that have been accepted that are led by first-time principal investigators, people who have never led a successful Hubble proposal before, are now making up 30% of the accepted proposals. So this is a really wonderful outcome. It means that, you know, and I think most of these review teams, they don't mean to be biased. They're not intending to, they're really trying to do a good job, but we all have a kind of intrinsic, I don't know, sense that we're more comfortable giving time to someone that we know than someone we don't. But this has shown that if you only look at the strength of the science itself and the proposal, it gives a chance for first-time new people to get involved and to get time on the Hubble telescope and do terrific science. So we're very pleased with that kind of innovation. I'm not going to talk about this part, but I'm really pointing to that side. So, all right, how do you keep a long-term mission successful? I think I'm going to skip all of that, but one of them, as I mentioned, is to keep the facility at the cutting edge of the science that people want to do and adapting it as science changes. And we hope that these telescopes will continue to inspire both scientists, but also the public. Here's an example of different ways that we have seen inspiration in our society coming from these telescopes. The student here is from the Maryland School for the Blind. So I spoke to a group of students who are visually impaired, but we gave them images from Hubble that have tactile coatings on them so that a galaxy feels different from a star, feels different from a planet. And so people looking or feeling these images are every bit as excited about what they're discovering as others are who look with their eyes. So making what we discover in science accessible to people is really important, and it's very inspiring to our culture. This image is from a church window in a church near the Johnson Space Center in Texas, where all the windows in the church are modeled after Hubble Space Telescope pictures. So you can go in the church and the light comes through and you feel that amazing sense of awe and inspiration. We also have moving trucks that are inspired by Hubble. And then this was an art event at the Space Telescope Science Institute where one young artist created this interesting piece based on Webb work. So inspiration hopefully will continue for everyone on the globe here. I like the way our field unites people. So I'll just close by saying that the Hubble Space Telescope mission will continue with strong scientific capability, likely through this decade, hopefully beyond, and its scientific capabilities, they complement other missions like probes, ground-based observatories, and missions like Webb and the upcoming Roman Space Telescope. The Roman telescope will be an infrared telescope, but it will have a much wider field of view. So it will be doing, surveying galaxies, surveying stellar populations and nearby galaxies with very much speed. And also by doing that, studying the interactions of dark matter and dark energy over cosmic time. Hubble sets the stage for a future, even larger flagship, ultraviolet, optical, and near IR mission, something we might call a super Hubble, that's now beginning to be designed. And it's now called, at least for now, the Habitable Worlds Observatory. It's designed so it will be big enough to take direct images of exoplanets, but also do all the other general astrophysics as well. So already there are working groups being formed internationally for the Habitable Worlds Observatory. If you want any more information on any of this, we've got great websites, nasa.gov/Hubble or /Webb, ESAHubble.org, ESAWeb.org. And these are some gallery sites for images, and we're very active on social media like @NASA-Hubble. And you guys have been so patient and you've waited so long, so I thank you for your attention today. Yes.
Thanks for the talk. Are there planned more missions from astronauts to the Goddard or that was it?
Well, the problem is we don't have the space shuttle program anymore. And so right now, NASA is developing a more sophisticated vehicle that will go farther than the space shuttle could go. So the new vehicles will go back to the moon, hopefully to Mars, but they're not ready yet. So we don't have the capability to do this. Now, there are many spacecraft that are, even commercial spacecraft, that are going to the International Space Station right now. But the space station is in a different inclination orbit from Hubble, and none of those spacecraft, including from private industry, have the capability for astronauts to come out and do extravehicular work. They don't really even have the capability, although they're getting better at this, to dock with another satellite in this kind of way we need for Hubble. So right now, we don't have any way of doing this, although I skipped over this, but there has been a study that we have done over the last year with a private company, SpaceX, that is thinking about, and we're thinking about, having a company like SpaceX or some other private company potentially go up, not to send astronauts out to do all the sophisticated work, but at least to boost it up a little bit higher. Because if we can get it back up to like 600 kilometers, it might give us another decade of science, if the science instruments will hold out. So really, we need to make Hubble last as long as possible. And then we need this new Habitable Worlds Observatory that will hopefully launch in 2040. And that will be Hubble 2.0. All right. Yeah.
So what's the fraction or public?
Well, okay, so this is the number of publications coming out every year. I don't know if that's what you're asking, but the ones that are, and I should have updated this. This is, I don't have last year on this, but it's the same trend. The new publications coming out of new observations from Hubble are in the red down here. Publications that are based on just the archive, pulling data out of the archive and finding something new and publishing that, is in the purple. And there's actually slightly more archival publications than new, what we call general observer observations. And then a lot of papers take some of both. They're based on both. So that's one answer, but maybe you're asking if there's much left to be done with the archive, and absolutely, I think people are finding lots and lots of new science, particularly these things I mentioned, that we're trying to put data in the archive that will be useful for all kinds of science, like the whole selection of ultraviolet spectra of all these nearby stars. We don't know what kind of science that's going to produce, but we want to make sure we have that baseline catalog there so that people can delve into it for whatever they need. Also, people are realizing, as I showed you some examples, that when you have 34 years of observations, you may be able to find temporal domain trends that the original proposers didn't intend for their science. But if you can look at that same field over decades, you might find all kinds of things going on, from exoplanet transits to protostellar jets changing their form to supernovae going off, all kinds of things. Or you can get higher sensitivity. One team actually used decades of archival data to find new structures and gaps in protostellar or in the debris disks around young stars to identify potential proto-exoplanets that wouldn't have been found had they not had decades of data to add together to get the sensitivity that they needed. So there's lots left to be done, and the archive is free to everyone.
Questions? Let's see if there is questions on the.
Well, let's see.
Zoom.
And look,
Yeah.
there's the chat. There is a question, and the question is, can you put on your camera? Okay. I'll be around all afternoon, so I'm happy to talk to you.
Okay, thanks. Well, thanks again to Jennifer.
Thank you.